Hello friends, welcome to the first lecture on the topic of short time Fourier transforms. So, this lecture is numbered 5.1 as per our convention. In this lecture, we are going to exclusively talk about the definition of short time Fourier transform and also look at the reconstruction property of the short time Fourier transform. Primarily, we will keep this lecture theoretical, but somewhere during the lecture or towards the end of the lecture, I will show you how to implement a short time Fourier transform in MATLAB using the time frequency toolbox. So, we will look primarily at definitions and the filtering viewpoint and then look at a few theoretical examples. Towards the end, I will have an illustration of the short time Fourier transform on an impulse like signal or a sine wave and so on. Okay. So, let us get started. I think we are familiar with the basic idea of the short time Fourier transform. We had discussed this in the introductory lecture as well. The main idea is to slice the signal into different segments so as to gain time localization and then subject each segment to a Fourier transform. So, that remains a basic idea. The rest are all flavors of this idea. Now, how I segment, what kind of window I choose, whether I am going to have overlapping or non-overlapping dictates what properties I get for the short time Fourier transform, particularly in terms of spectral leakage or orthogonal representation or redundant representation and so on. In this lecture, we are not going to study the effects of different windows or window lengths and so on. We are just going to touch base on those ideas. There is the separate lecture which will talk about the practical aspects of the short time Fourier transform, wherein we will also talk about the discrete time short time Fourier transform. So, this and the next lecture will primarily be theoretical, but of course, give us lots of insights into how the short time Fourier transform behaves for different windows and different signals and so on. So, let us get into the math here. First of all, slicing is equivalent to windowing the signal with a finite width window function. That is the key. Now, we require these window functions to be of finite width, obviously because we want time localizations. You can imagine the regular Fourier transform to be the short time Fourier transform. In fact, it is a long time Fourier transform. The window functions are infinite in length. So, I can represent now the sliced segment of the signal as x of tau comma t. T is a general function of time that we have been using. Now, tau is the center of the window function that I am going to use. At the bottom of this slide, I show you examples of 3 examples of window functions. The first 2 are both Gaussian window functions, while the last one, that is on the bottom right, is a triangular window function. The difference between the first 2 is fairly obvious. The first one is a narrow window function, that is of shorter duration than the second one. And in the third one, I have a triangular window just to show you that the difference between triangular and Gaussian is this abrupt beginning and end of the window function, whereas with a Gaussian window function, I have smooth beginnings and ends, and typically these are the kinds of window functions that are preferred. If you look at the literature on the window functions, you will find the discussions on window functions both in the short time Fourier transform literature and more so in the Fourier transform literature, where the window functions are used to mitigate spectral leakage. Recall this concept that we discussed in the context of Fourier transforms. There you will find that these windows are preferred simply because of their smooth taperings at the beginning and end. The sharp or the abrupt beginning and end introduces some kind of artificial discontinuity. So, you want to be kind to the signal at the beginning and the end, right. And we will talk more about this when we talk about window functions. One of the key requirements of this window function is that it should be real valued and symmetric. Why symmetricity and so on, we will talk about it later on, but we want it to be symmetric. Now, notice that again tau is the center of the window function. So, what we are essentially going to do is pick any of these window functions. I am going to, let us say, pick the first one. I am going to place this window function in such a way, that is at the beginning of my analysis, in such a way that the center of this window will coincide with the start of the signal. Okay. So, that means initially tau is 0, and then I traverse along the length of the signal. In practice, I am going to have sample data. So, the question that arises is, how am I going to march forward in time? Am I going to march ahead one sample at a time, two samples at a time, and so on? That dictates whether I am going to generate a redundant representation or an orthogonal representation, and so on. If I want a dense representation or a dense short time Fourier transform, then I would march one step ahead, one sample at each time. Then my tau will increment in the same way as the time instant itself. In this lecture, we are not going to talk particularly about sample data. So, we will postpone the discussion on what values tau will take on the discrete in the discrete time, but as of now tau will run from minus infinity to infinity, for example. So, that is just a theoretical discussion, or if your signal begins from 0, then it runs from 0 to infinity. Okay. So, now having mathematically defined the slice signal, I can define the short time Fourier transform, which is nothing but the Fourier transform of the sliced segment. This is one viewpoint. Very soon we will talk about an alternative viewpoint of the short time Fourier transform. So, the only difference between the classical Fourier transform and the short time Fourier transform is this windowed segment that is being used in the short time Fourier transform vis-a-vis the original signal in the classical one. Now, also in place of omega, I have this symbol z. This z is nothing but the center frequency of the window function, and I will talk about it soon. I will show you also what the center frequency means. So, essentially tau is the center of the window in time, or you can say the mean location of the window function in time, and z is the mean frequency of the window. So, what we are doing here is I am taking a Fourier transform of the slice segment around a center frequency z. Now, my time axis of course runs from minus infinity to infinity, because I am looking at a theoretical problem. So, now I have substituted for x of tau comma t here, I have expanded it. Now, my window function appears. The nice thing about this integral is I can write this as an inner product between x of t and a function g with subscripts tau comma z, and that g is a function of time t. What is this g? This g is nothing but the product of the window and the complex sine wave that I have. In fact, once again you can realize or recognize that I recover the classical Fourier transform if I replace this g simply with the complex exponential itself. Okay. So, that is the difference again between the short time Fourier transform and the classical Fourier transform. We will talk about this g more in detail in the next slide. So, this g now is called what is known as the short time Fourier transform atom or the time frequency atom, and the entire short time Fourier transform is believed to now be based on a decomposition on this time frequency atoms. In the Fourier transform, the premise is that I can decompose my signal on sinusoid atoms, that is complex sine wave atoms. Now, I have this what is known as a time frequency atom. I can reconstruct my signal. In other words, here this is my analysis equation, and here now I have my synthesis equation. Given the short time Fourier transform, I can always recover the signal using this expression here. Pretty much this is a two-dimensional extension of the one-dimensional recovery expression that I have for the continuous time Fourier transform. Once again, what I have done here is I have replaced this short time Fourier transform with again the result that I have. It is an inner product between the signal and the time frequency atom or the short time Fourier transform atom that I am using. Now, notice notations here, I have lower case for the signal and the upper case for the transform itself, and once again the short time Fourier transform is a function of two parameters, tau and z, whereas the classical Fourier transform was a function of a single variable, which is frequency itself. This tau and z have the units of time and frequency. They are now the center in time of the window and center in frequency of the window. So, they are actually centers and not necessarily just time and frequency themselves. Okay. So, let us take an alternative viewpoint of the short time Fourier transform based on this concept of short time Fourier transform atom that we just discussed. So, what is this alternative viewpoint? In this definition in equation 2, we said that the short time Fourier transform is the Fourier transform of the windowed segment. The alternative viewpoint is that the short time Fourier transform is the transform of the signal itself, but now with a clipped sinusoid. So, you should appreciate both these viewpoints. In one viewpoint we are saying I am going to clip the signal and then take the Fourier transform of the clipped signal. The other viewpoint says no, I am going to keep the signal as is, but I am going to clip the basis, or I am going to clip the analyzing function. That gives us some different insights into how the short time Fourier transform works. So, this clipped sinusoid is what we had introduced as G earlier. It is a function of tau and z, that is, it basically is a function of where the window is located in time and where its Fourier transform is centered in frequency. All right. Now, earlier I showed you window functions, that is, I showed you what this W's can look like. Now, I am going to I am showing you here how the G's can look like. So, all I have done is I have taken those three window functions that I have shown you earlier and multiplied them with the sine waves. I am just going to show, I am going to show you only the real parts here. So, the Gaussian window earlier that we saw of narrower width is multiplied by this complex sine wave, and likewise this Gaussian window and the triangular window as well. So, these are my analyzing functions. I am going to really measure what is there in the signal using these atoms. When the local feature, that is a segmented part of the signal, matches, or I can say when the signal itself matches with this atom. Remember, now the viewpoint is that I am going to analyze the original signal. I am not now looking at a clipped signal. I am going to analyze the entire signal with this atom here. So, for the purpose of discussion, assume that your signal exists as long as I have shown here for the window function itself or the atom itself. Then imagine that I bring a signal here and analyze that signal with this atom. Obviously, where the analyzing function of the atom is 0, it will not be able to detect what is happening in the signal in the corresponding time portions. It will only be able to analyze the signal where the atom is active, right, where the analyzing function is active. That naturally gets me the time localization or it gets me the local features of the signal in time. And question is now, what about the local features in frequency, right. So, it is clear now how these atoms are able to get me the local features of the signal in time. For that, we will discuss the duration and bandwidth of the atom itself shortly. Before we do that, it is nice to talk about the spectrogram, because that gives me the energy density of the signal in the time frequency plane. How do I define the spectrogram? Earlier I had told you this in the previous lectures, that the spectrogram is nothing but the squared magnitude of the short time Fourier transform. Now, the equation 5 here gives me the basis for defining the spectrogram as a squared magnitude of the short time Fourier transform. So, I have here on the left hand side the energy of the signal defined in time, and by virtue of Parseval's relation we have seen this expression before. This is the energy in terms of frequency domain variables or Fourier transforms. And now, by virtue of Parseval relation, I can also show that the energy is preserved in this manner. So, the area, the two-dimensional area under the surface of the squared magnitude of x of tau comma z gives me the total energy, and x of tau comma z is a continuous function. Notice that tau and z are continuous functions, right, continuous valued variables right now. Therefore, the squared magnitude of the short time Fourier transform qualifies to be an energy density in the time frequency plane. Main requirement is the area under this spectrogram should give me the energy, and that is exactly what equation 5 is establishing. So, we will use this spectrogram extensively to analyze signals, and that is how people it has been used in the literature for analyzing the frequency content of the signal as a function of time. Okay. So, let us briefly talk about some theoretical requirements on the window function. We have already said this. I can't use any window function that I like. By window itself, it gives us an idea that it has finite duration, and that is exactly what we want. Technically, we say that the window should have compact support. This is a technical term to indicate that the window exists only over a finite period of time and vanishes outside this interval. So, the window should decay in such a way that x of tau comma t should be this for t near tau, that is near the center of the window, and 0 for t far away. Basically, this says that I can have my window function decay exponentially, it need not abruptly go to 0 also. So, such window functions are also being accommodated, and obviously, I want the window length or the width of the window to be much shorter than that of the signal, otherwise the entire purpose of computing the short time Fourier transform is defeated. If the window is as long as a signal, then it is nothing but the Fourier transform. So, that is more of a common sense requirement, and typically we normalize the window functions to have unit energy, so that I have energies preserved. So, that is important. You should indeed verify that the routine that you are using is in fact normalizing the windows to have unit energy. If you are writing your own routine to compute the short time Fourier transform, this should be one of the primary steps before you evaluate the short time Fourier transform. Okay, so, let us return now to the discussion that we had on the time frequency spreads of the window. We said that tau and z represent the centers of the window in time and frequency. And why is that? So, tau, it was obvious why tau is the center of the window in time. Now, let us look at this atom here, time frequency atom. Although I said spreads of the window, ideally I am talking about the spread of the atom itself. So, that please note that correction. So, this is the atom that I have, the time frequency atom, and its Fourier transform is given by this. It is e to the minus j tau times omega minus z times the Fourier transform of the window shifted by z, right. So, this w, big W is nothing but the Fourier transform of the window function, big G is the Fourier transform of the atom itself. So, the only difference between the Fourier transform of the atom and that of the window is this factor here, but as far as the magnitude is concerned, they are the same. Now, it is clear from this expression here in 7 that the Fourier transform of the time frequency atom is centered around z. This expression itself clearly tells me that the center frequency is z. Therefore, now I can compute the time and frequency spreads of the window function. Why do I want to compute the time and frequency spreads? Because the role of this window function is to get us the local features of the signal in time and frequency. Now, I want to know what is meant by local. Local is a very qualitative term. For a given choice of window function, I want to see what is the neighborhood of the window function in the time and frequency plane. Is it very vast? Is it going to get me the features of the signal in a small neighborhood or a large neighborhood? What is exactly the neighborhood of the signal that it is looking at in both time and frequency? And that is why we are defining or we are analyzing the time and frequency spreads of the atom here, rather than, as I said, instead of window function, think of the atom. So, this is the duration or the squared duration of the time frequency atom, and this comes from the definition itself. By definition, we have recalled the definitions of duration that we had for any signal. So, you can think of the time frequency atom as another signal itself, whose center is tau and whose energy density in time is given by this. Now, by a simple change of variables and by substituting for g this expression here, I can simply rewrite this integral as integral t square modulus w of t square. Why did I do this? To show and to recognize that the duration is independent of the center. That is, the spread of the window in time has got nothing to do with where it is located, where its center is located in time. So, as I am traversing in time, it has the same window spread, it has the same time spread. Likewise, now for the spread of the atom in frequency domain, I invoke the definition and then once again I rewrite this in terms of the window function itself. It turns out that it is just because I have chosen the atom this way, I can rewrite this way. It is not that it is true for any time frequency atom. Only for the short time Fourier transform I can write it this way. Once again I see that the spread in frequency of the window of the time frequency atom is independent of where it is in the frequency plane. That means it is going to actually extract the signal features in the frequency plane over the same neighborhood, regardless of whether you are looking at low frequencies or mid frequencies or high frequencies. So, let me illustrate this to you. This is something that you will also see in Mallet's book. We will now henceforth frequently refer to Mallet's book as well. This kind of schematic illustration of the time and frequency spreads of short time Fourier transform is fairly common in the literature. The main message that we get from the previous analysis is, foregoing analysis, is the time and frequency spreads of the short time Fourier transform is uniform across the time frequency plane and is independent of the center time and frequency of the window function. So, this is the time frequency plane. The x axis or the horizontal axis is time and the vertical axis is frequency. I have this window function, just a symbolic one, in time which has a certain width and its width is characterized by sigma square t. Remember, the width of the window function is not sigma square t, it's only sigma square t is only a measure of the width. And by the duration bandwidth principle, I know if I choose a wide window such as this, it is going to have a narrow bandwidth, that is in narrower frequency spread, which is measured by sigma square omega. So, when I move to analyze the signal in time domain this way with this window function, wherever I go does not matter. Let us say I move along frequency axis instead of time. So, I want to get the local features, I want to extract the local features of the signal in the frequency domain now. So, I am asking what is the frequency content in the low frequency regime and the high frequency regime. Even as I move upwards, the same window spread in frequency domain and in time domain exists. It is not adjusting itself like the way it does the wavelet transforms to. Remember, the wavelets are specially designed in such a way that when you are looking at the low frequency regime, you use wide wavelets, and when you are looking at the high frequency regime, that is when you filter the high frequency content of the signal, you would use narrow wavelets, but that is not necessarily the case with short time Fourier transform. The reason being, look at how the short time Fourier transform is evaluated. I window the signal and then I match this windowed signal with all frequencies possible that I know. But then simple practicality or common sense tells me that if I have windowed, if I have chosen a slice of the signal, then there is a limit to which I can detect the frequency content. The limit being that at least that particular slice should have completed one cycle, right. So, if I am choosing a very narrow window, then I should not be really examining the signal for the low frequency content, because the low frequency, if there was a low frequency component, it would not have had the opportunity to complete one cycle in that narrow segment of the window. So, a judicious choice of would be to only examine if I have a narrow segment for the high frequency content, and if I have chosen a wide segment, I would choose to analyze only the low frequency content, but that is not what is happening in short time Fourier transform. I am analyzing, does not matter, regardless of the width of the segment that I have chosen, I am going to analyze it for all frequencies, and that is what is the consequence of this uniform spread in time and frequency across the entire time frequency plane. And this will become more obvious, that is you will be able to appreciate this better when we talk about the wavelet transform as well. All right. So, this also leads us to the filtering perspective of the short time Fourier transform, and in fact, it will reinforce what we have just discussed. What we are doing here is we use the definition of the short time Fourier transform and rewrite it deliberately this way. There is nothing that we have lost, we have just multiplied and divided by this factor e to the minus z tau, and now we can rewrite this integral in this way. Remember that this integral is in the convolution form. It is a convolution of x with the time frequency atom, right. The time frequency atom being w of t times e to the I z tau. So, it is a convolution of the signal with this w of t times e to the z tau, and therefore, x of tau comma z is nothing but the product of x of omega times g of omega minus z times of course e to the minus j z tau. Yeah. So, now all of this is mathematics, but what is the interpretation that I have here? Well, short time Fourier transform, what it gets me is actually the local features of x in the frequency domain centered around z, and it does not just get me x of omega centered around z. This x of omega is being multiplied by g of omega minus z, right, by this function which is not unity in the vicinity of z. It will have its own shape, right, and that is the problem that I have with the short time Fourier transform, but also it is a nice thing, it tells me that the short time Fourier transform acts as a filter. So, let me just illustrate this to you on the board. So, what is happening is, let us assume that x of omega or the magnitude of x of omega in general is a complex number. Let us say it looks like this, and let us say I am interested right now, I am looking at some value of z which is here. So, this is what is the x of omega. What happens is, ideally I would like to get exactly x of omega around the center frequency as is, whatever is the magnitude of the Fourier transform of the original signal in around this neighborhood, in this neighborhood of z. Unfortunately, this result tells me that I am not going to exactly get that, it is going to be multiplied with a window which will actually look like this if it is centered around z. So, this is the magnitude, let us say magnitude of the window of the g that I have, or the window itself. There is no difference between the magnitude of g and w, we have seen that earlier. So, I might as well say this is the window itself. So, what I have is typically I choose a window that has finite width, we have discussed this earlier, that is the purpose of short time Fourier transform. As a result of which the window function will have some spread in frequency domain. So, let us say it has this kind of spread in frequency. Let me just write the w of omega itself. Now, this is, let us say, centered here, it has a center frequency of z. So, what is happening is this x of omega here is being multiplied with w of omega minus z, as a result of which I am not going to exactly get the local features of x of omega, it is going to be distorted by this factor. And that is the distortion we have seen and we have talked about earlier, and we will see numerous examples. Remember, I said if I were to analyze a sine wave using the short time Fourier transform, ideally the sine wave we know has a peak in frequency. If this is time, this is omega. Ideally, I should be able to get this kind of a line in the time frequency plane for a pure sine wave. But if I were to analyze the sine wave with a short time Fourier transform, then I would see a band instead of a line, and this band is essentially because of that. So, what is happening is the short time Fourier transform is filtering with a constant bandwidth, but it is this bandwidth ideally is not the one that is suited for a sine wave, all right. It is this bandwidth is coming about because I have chosen a window of finite width, all right. So, the interpretation is that essentially the short time Fourier transform at tau comma z is a signal filtered by this w or g. In fact, I use g and w interchangeably because magnitude wise they are one and the same, all right. By the way, in deriving this equation 9, we have used the symmetry property and the convolution property of the Fourier transform. So, ideally it is desirable to have this w as a Dirac, so that I get, even though I pick a small segment of x of t, I just want whatever is truly the frequency domain characteristic of x of t in that window function. But this result in 9 tells me I am not going to get that, I am going to get a distorted version of what I see locally, all right. And that is again by virtue of the duration bandwidth principle. So, the two key things that we want to analyze, that is the primary property that we want to analyze is the time frequency resolution. How well does this STFT resolve the features of the signal in time and frequency plane. For this we take two test signals, which is the Dirac delta function, that is if I had an impulse, how would the short time Fourier transform behave? Well, I just put this impulse through the definition of short time Fourier transform, and I notice that the short time Fourier transform is nothing but w of tau minus t naught times e to the minus j z t naught. Now, this is thus the time resolution is essentially the effective duration of the window. If I choose a wide window, then I will be able to resolve accordingly. If I choose a narrow window, then I will be able to resolve accordingly. If I have to resolve an impulse, common sense tells me I have to use a window of very, very narrow width, ideally of one sample, but that is not possible. Even if, so what happens if I do that? I have problems resolving complex sinusoids. Signals are not going to be present with a single feature, they are going to have a mix of features. So, these are the two extreme features. The Dirac delta is extremely localized in time, and the sinusoid is extremely highly localized in frequency. In the case of sine wave, as I just discussed on the board, when I plug in the sine wave into the definition of the short time Fourier transform, I get this expression, x of tau comma z is w of z minus omega naught is the frequency of the sine wave that I am using. So, what does this expression tell me? It tells me that the way the sine wave manifests in short time Fourier transform depends on the Fourier transform of the window itself. And we know that this window is not going to be Dirac in the frequency, it is going to have some finite width, which means my sine wave is going to be distorted in the frequency domain. So, the impulse is also going to be distorted and the sine wave is also going to be distorted. If I do not want the impulse to be distorted in short time Fourier transform, I have to choose a very narrow window. But what would happen if I choose a very narrow window? Its spread in frequency will be very large, as a result of which I will not be able to localize the sine wave very well. If I want to localize the sine wave, I need a window which is highly localized in frequency domain. By the virtue of the duration bandwidth principle, if I have a signal which is highly localized in frequency, it should have infinite spread in time. Then I will be unable to get the local features of the signal in time. So, this is a trade off that is involved, all right. So, a simple example that I want to take is for a linear chirp. We have discussed two extremes. Let us look at the linear chirp, and this is an example taken from Mallet's book. This is the chirp. You can see that it is a linear chirp because the phase is a quadratic function of time t, and I am using a Gaussian window. This is exactly the window that Mallet uses in his book. And if you work out the math, then the spectrogram turns out to be having this expression here, all right. Now, the reason for picking this example is to illustrate a point that we will discuss more in detail later on. Look at this expression for the spectrogram for a linear chirp. At a fixed time tau, tau is the center of the window, but that is also the time. At a fixed time tau, this spectrogram reaches a maximum when z is 2 alpha tau. Alpha is a feature of the signal here, tau is the time that you are looking at, and z is the frequency at which you are situated in the time frequency plane. So, it says this spectrogram reaches a maximum in the time frequency plane at a given time tau when the frequency is 2 alpha tau. Now, this 2 alpha tau is also the derivative of this phase here, which means it is nothing but the instantaneous frequency of the signal. Recall the definition of instantaneous frequency, it is a derivative of the phase, right. So, what is happening here is that the maximum at any given time tau, at whatever frequency the spectrogram reaches a maximum, it happens to be the instantaneous frequency. The question is if this is a coincidence, or in general is this true that the maxima of the spectrogram will give me information on the instantaneous frequency, will give me estimates of the instantaneous frequency. It turns out that this is not a coincidence. There is a very nice result which states that the maxima, local maxima of the spectrogram in the time frequency plane gives an estimate, a good estimate of the instantaneous frequency of the signal, and these local maxima are known as ridges, and we will talk about it later on. Okay. So, with this we come to a closure of this lecture.